Okay, so my screen is visible, yeah? Alright, cool. So, welcome back, ladies and gentlemen, boys and girls, to the XRD lecture series. So, the last time we just went over an overview, and in the overview there was a mention of crystallography. So, in this lecture, we'll go over what are basically the basics of crystallography. But do note this is a very, very oversimplified, very generalized, overview of it. I do intend to revisit this topic, this entire subject in the future lectures. Okay, let's begin. Okay, so before I start, what I'm going to do is I'm going to show you some pictures of what crystals are perceived to be, and I want you to see these two pictures. Do you think these two are? Do you think these two pictures, these two substances, do you think these are crystals? Yes or no? Likewise with these two powders here, and likewise with these two pipes. Okay. So now let's begin with a definition of a crystal. So a crystal is a solid composed of atoms, ions, or molecules that are arranged in a repeating and ordered pattern. So it's periodic in nature. And as you can see in this figure here, this is what a single crystal looks like. And as you can see, it's regular and it's repeating, and it's in the exact same direction here. A polycrystalline is also regular, but see how they're oriented differently. So if you look at like a sort of like an SEM or something like that, you'll see something called the grain boundaries. There'll be a boundary here between these phases. And this is the amorphous, and you can see it is randomly oriented and is short ranged here. But the thing with crystals are what makes them unique amongst other solids, so like in comparison to let's say glass or an amorphous substance, is that there are certain symmetry relationships in the arrangement of the crystal. So now let's talk about the field itself, crystallography. It's pretty straightforward. It's just study of crystals and its properties. But when it comes to X-ray diffraction, what we're discussing is we're looking more into its geometry. Okay, because in the JCVDS card, you mainly see like geometric aspects of the crystal. So now let's start with our crystal structure. So our crystal structure is composed of mainly two parts. One is the lattice, the space lattice, and the other being the basis. Just to quickly go over what lattice is, a lattice is basically an infinite number of points that are equally spaced. Okay, our basis is basically what we use to represent these points, and the basis can be an atom, a molecule, or an ion. Sometimes you'll see this word basis with motif. And when you combine these two things together, we get our crystal structure right here. Now, let's quickly discuss the concept of the Bravais lattice. And yes, I did take this from Ashcroft and Mervyn, if you can't tell. So just to quickly go over it. So remember how we looked at the space lattice? So if you want to extend the section of the space lattice, we can look at it from here. And if we look at these position vectors, so this is our position vectors A1 and A2, and put on my charger. So it says here that we have these vectors. So these are our space vectors. Sorry, our basis vectors A1, A2, A3, and these are the integers N1, N2, N3. And when we use these position vectors, we can construct our unit cell. So this is our unit cell in 2 dimensions. And there should be an angle here, but I guess it must have missed out. Book by B equality. So this is in 2D, and we have our vectors A and B. This is in 3 dimensions, and we have our what's it called? Our lattice parameters, our basis vectors A, B, C, and these are our interfacial atoms, alpha, beta, and gamma. And this is another unit cell. You will also see this one. It's called the Wigner site cell. So what's the difference between the Wigner site cell and this one? So this is what we refer to as a primitive unit cell because there's exactly one point to this lattice point here. Whereas the Wigner site cell is composed of one point, but you have all these different points built around it. So that's why it looks like this. So this is our Bravais lattice in 2 dimensions, and there's like 4 possible shapes because one of the things about the Bravais lattice construction is you have to fill this space in such a way that there are no voids and there are no overlaps. So in the case of 2 dimensions, we only have 4 shapes, and we have 5 Bravais lattices. And as you can see here with the square, the lengths are the same, and we have the angle, which is phi, that is 90 degrees. And here it's 120, and so on and so forth. This is in 3 dimensions, and in 3 dimensions we have 7. And as you can see, with our lattice parameters here, which is A, B, and C, and with our angles, which is alpha, beta, gamma. And with these crystal systems, we have 7 of them. That means we have 14 Bravais lattices instead. So I will also like to discuss the symbol notation here. So commonly, let's say we take this simple cubic because as that's the simplest one here. P is referred to as simple or primitive. I is your body centered, and F is your face centered. Now for certain other ones like your orthorhombic here, which has this base center here. So that's why this is a C. And for a rhombohedral, which has its own sort of Bravais lattice, is R. All right. So now, if you want to discuss about these Bravais lattices, I've taken it again from Kittel, and from Kittel you can see these are the information. This is the information regarding the cubic system: simple cubic, the body centered, and the face centered. So now let's discuss about the Wheeler indices. So we have to figure out how do we notate the planes and directions within the crystal lattice. So there will be some kind of intersection, right? So when we construct it, we have to find out how to notate them. So this is where the Wheeler indices come into play. So this HKL, these are your values here. So this is from taking the intercepts. This is for a single plane. And do note that there are no commas here. So you should not put commas here. This is how it's notated. This is for a single plane, and this is for direction. And these ones are for family of planes and a family direction perspective. So now, how do you find them? So you have to find the intercepts on the axis in terms of our lattice constants, or basic vectors, A, B, and C. And then you have to take the reciprocal. And after taking the reciprocal, we have to find the smallest possible integers. So you have to reduce them. So you take taking the lowest common multiple. So this is what they look like. So this is 1, 0, 0. Draw this out. So if you want to know some rules, if it's parallel, it will be for the Miller indices for like a parallel plane would be 0, which in this case would be infinite. Okay. And if you want inversion, which should look like this, there's a mistake here. So if it's a negative, we'll learn to something like this. It should look like this. Okay. Which is what this bottom one is depicting here. And these ones are showing all the directions. So this is like 2 bars. So this is the inverted, and this is 3 and 3 here. So next part. Now we have to discuss the symmetry operations. The reason being, remember, we have defined the crystal to be symmetric in nature. So since we have defined it to be symmetric in nature, we have to show that, in fact, it is symmetric. And this is where our symmetry operations come into play. So what are these operations? These are operations when you carry out on an object, so in our case, our lattice, it leaves the lattice looking exactly the same, even after you carry it out. So there are 4 symmetry operations. They are translation, rotation, mirror, and inversion. So what is our translation? So our transition operator just involves shifting that object by a certain amount, and when you shift it, the object remains the same. So if I move the lattice by a certain distance, that lattice should not change, right? And do note this translation property is really important for the next one, which is our rotation. So when we rotate our object by about some axis, the object should not change, right? It should remain exactly the same. But here's the issue. Due to the fact that we have said that the Bravais lattice, the space should be filled, but there should be no voids and no overlaps. There are only a certain n-fold symmetry that can be done. And this is a pentagon. Do you see all the voids here? Yeah, this is impossible. So as a result, we only have 2, 3, 4, and 6. And these are our graphical symbols for each of these rotations. The next one is mirror, and just by visualizing what's happening here, you're just taking the mirror of the object. The symbol for a mirror is just this. It's just the letter M. And the next one is inversion. So as you know what inversion is, if I take, let's say, an X and I invert it, so it becomes minus X, right? And you can apply this inversion to your rotation and to your mirror. So as a result, you get, let's say you have 2, right? This is our rotation. That means this is 2-fold rotation. If I put this bar here, it's become an inversion. You see that? This is how it becomes an inversion. The next part I'm going to discuss are point groups. So in a point group, what happens here is that one of the points will be fixed. So any point, given its center or whatever, it will be fixed. And as a result, there's no translation involved. So it's purely rotation, reflection, and inversion. And from this, we know that there's 32 point groups, and this is exclusively for 3D. So, and the next part is about space groups. In the case of space groups, we combine the translation symmetry along with the other ones, with our Bravais lattices, and we have 2 terms now. We have our glide plane and we have our screw axis. So I'll just quickly go over what these 2 are before I come back here. So the glide plane is basically translation plus reflection, and the screw axis is translation plus rotation, and this is like a pictorial representation of the glide plane here, so you can see what's happening with the feet. And this is with the screw axis. So here, this is showing fourfold, but see now there's a translation of 3 here, and that's the reason why it works like this. And this is just an inversion. And you can tell this is screw axis because of this tail here, which is what you see in this next picture. And this is a representation of our glide planes. So from here we get 230 space groups, and this is for 3D systems. Okay, so if I'm gonna, I'll write some examples of a point group. So this is for a cubic system. So for a cubic system, we have this. So you have these 2 examples here. I'll quickly write this out. All right, so these are our point groups here. So this is just a inversion. This is our mirror, and this is the rotation. And these 2 are just plane rotations here. This is for a non-central symmetric. If it's central symmetric, we get this. Do note this is for cubic only. For other ones, I will have to check for that. I don't recall. If you want for a space group, so shoot, one sec. Where's the eraser gone? Get the eraser. Wait, where's the pen? There you are. Okay, this is our space group. So basically, how do you know it's a space group? So this is our Bravais lattice here, and these other 3 are just your symmetry operations. So there isn't a whole lot of physics here. The only reason I've gone with this is because you will see this a lot when you look at the when you look at that JCPDS card. And unfortunately, I did miss out on some examples. I was supposed to show some process structures, but I did face some issues with certain topics here. So hopefully, I've given everyone here some insights into what crystallography is. I hope people would look into it further. I do intend on again giving a more detailed seminar on this. So what I'm going to do is I'm going to take like a small break if that's okay with everyone here. Yeah, I'll continue in 5 minutes. Give me a second. Sorry.
Bro, who is teaching Miller indices?
Sorry. Wait, who asked this question? Who's teaching what?
Are you going to teach Miller indices?
Yeah, I already covered that. Why? What happened? Do you want me to go over it
No,
again?
no, 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 it's fine.
All right. Okay. Someone asked a question. What is the optimized crystal packing, like the highest number of atoms per unit volume slash density? Okay. Memories, I think it's
Is it rhombohedral?
no. Don't think so. One second. I should have mentioned hexagonal close packing. I forgot to mention that one. The the one that I have here in the cubic one is FCC. So I should have actually checked for HCP, but I think I'll just go with FCC for now. So yes, that is correct. It is face center cubic. Yeah. Again, I'm going to double check this. I have to check for HCP as well. I'm not gonna do that right now, but I'll let you know if HCP is slightly higher than FCT. Excuse me.
Someone speaking?
No, nobody's speaking. Again, I'll be frank with everybody here. I did find this rather tricky. A lot of it just because it's just very in depth. There's a lot to read. There's a lot to go over. And the other thing is, a lot of it is just mathematics. There isn't really any physics going on here. This is maths, right? This is like group theory mainly. But it had to be done because without it, you wouldn't really understand how to analyze the data, right? So that's why I did it. Yeah, we resumed like a while ago. Someone asked a question. Oh shoot. Okay, I guess there must have been a bit of a miscommunication there.
Why why
I did.
why hexagon? Why
I
hexagon is the most efficient shape?
I don't know. I don't know that. I'm not sure, man. I'll have to double check. What do you mean by most efficient shape? Are you saying efficient as in it has the highest packing fraction or what?
No, no, no. The most efficient shape in this world is the hexagon. Like, have you seen the nectar of honeybees? Like, it's hexagonal shape.
Yes, I've seen them. Yeah.
Yeah. In that sense.
I don't know how to answer that question, my guy. I don't know.
So, okay, it's fine, bro.
All right.
Can we talk about another topic?
Okay. What do you want to ask about, man? Look, I
From scientific
Can we
point of view,
maybe stick to the topic because this was supposed to be an event for players talk. So if you have any questions about the talk, then feel free to ask that.
okay, so we can only ask question based on crystallography.
that is correct. Yeah, because that's what the title of the talk is. It's literally
Okay, okay,
dubbed
okay.
as Basics of Crystallography. Okay, I guess I must have confused you in the beginning. Maybe I'm not sure. Oh, I'm sorry. Okay. Does anyone have any questions? Wait. Okay, we have some problems. Share some slides if anybody has any problems with some of the slides here. I mean, it is rather unfinished. So. I don't know. I mean, I'm not sure if anyone has anything to ask me or anything to say. Uh, would you like me to end it? Because I can if you want. Will you upload the PPT? Because I came late. Yes, I will upload the PPT. Uh, but this PPT is really bad. I'm not gonna I'm not gonna send it as it is, man. What I'm going to do is I'm going to have to like flesh out a bit more and then send it instead. I'm not gonna send this. Uh, One thing I would like to point out here is for the people on here, I have actually left the chapters that I used for this one. It's in the form, right? If you go to the what's it called? Let me check the name one more time. If you go to the event planning and you check for seminar and crystallography basics, you'll find out the chapters I used. Although I think this was exact, that I think hexagonal. Would you mind going over the point groups thingy once again? I was a bit confused. Okay, let me just get to the thing. Okay. All right. 1 second, ladies and gentlemen. Sorry. Okay, so point groups. Okay, can you tell me which part you're a bit confused by? Exactly. Like, where is the confusion? The numeric nomenclature. Oh, that's in the Miller indices. Okay, okay. Let me go back. All right. You know what? Let's go back to the Miller indices situation. Okay, let me go back to the Miller indices. Okay. All right. Okay. So, no problem. No problem. Okay. So the thing is that the Miller indices are integers, right? So since they're integers, you can't have decimal points. And when we represent the plane, right? This is about planes here, and essentially we want to represent we want to index the plane. So this is why we have Miller indices. These are like really simple ones. If you want a more complex one, if you want something like 111, right, as a plane, if I could get my little thing. Let me get my. I'll draw a very rough version of this. Um, okay. This is extremely rough, so I do apologize for this. I am using my mouse pad right now. I know my mouse doesn't work either. Nothing seems to work here. My mic doesn't work, so I'm using my laptop mic, which is a issue for me because I have to bend over whenever I talk. So here's our cube. All right, we normally represent these in cubes because the unit cell is simply represented like a parallelepiped or like a cube. So all right, let me just do it like X, Y, Z here. And for 111, so here, because remember the maximum here is 1. That's the maximum direct vector here. Z is also 1, this is also 1. And when I join these together, we will have our plane, which is 1, 1, 1. This is our plane here. And this is the direction that's showing 1, 1, 1, 1, 1, 1, right? That's the direction up here. This is the direction. Okay? And if you want a reciprocal, so let's say you get some reciprocal like this. So let's say we get our intercepts like this. So because earlier I was trying to explain this idea, right? So I'll show you an example. So let's say we have these intercepts right here. Okay? These are our intercepts. Yeah, you can say that, like coordinates. So these are our intercepts here, and what I'll do is take the reciprocal. So when I take the reciprocal, I get this. Now the next step is to reduce the numbers. So how do you reduce it? Well, there's one way. We can divide this by 4. When you divide this by 4, we get 1, 2, 4. This is now our Miller indice. Sorry, Miller index. Okay, I keep making the mistake of saying indices because indice is plural of index, right? So I should be saying index here. So this is our Miller index now. That's how it works. And if you want like a -1, it's just a bar. You don't put minus in. It's a bar here. That's just a notation that's used. How do these help us? Okay, I'm glad you asked this. Um, I guess I can mention this. You can use this to calculate interatomic distance. There's a formula you can use, which I will spoil a little bit. Let's see if I can remember this correctly. So it's something like this, if I remember. This is going to be in the next lecture, which will be on X-ray diffraction. Or is it like distance? No, it's not like that. No. So this is the interatomic distance d. This is our lattice parameter a, and these are the values from HKL. This is for a cubic system. So you can use this in XRD analysis, which is in the next section. So that's one way how Miller indices can be used. Or are they like distance? No, it's not. It's not distance. It's not between 2 points. Okay. Uh, you got XY. Okay, that's just a notation, man. Okay. What, do you want to use? I can use ABC. It's still the same. Okay. You can still use that. Excuse me. Someone mentioned that the visuals don't really work. I mean, that's fair. I understand why you're saying that. But, I do wish you actually put this in this chat. Will you going over the mathematics in the next lecture? No, not particularly in the next one, but in the future. Because the next one I've decided to go specifically for X-ray diffraction, so there will be more physics than maths. Yeah. So I think that's all, right? Or are there any more questions? I'm just gonna wait for someone to type out their question or whatever. All right. See you soon, man. Okay. Thanks for all of you for attending. I do apologize that this is not what you've expected. I do want to do this again next time, maybe in the future. Hopefully, by then I should have a much more fleshed out PPT, much more fleshed out talk rather than this, which is rather rough. Okay. Okay. Sorry. One more question before this thing stops, right? Which is, can you give a little insight into the next session? Are you going to talk about your research as well? Can I give a little insight? The next one, I think I mentioned it, is it's actually about X-ray diffraction. So one big term is Bragg's law, right? That's the biggest part. There's also going to be a talk about reciprocal lattice because I omitted the reciprocal lattice from this one. It's mainly because when I learned it in university, we always combine reciprocal lattice with Bragg's law. So I'll also cover that too. Regarding my research, I would rather keep that to myself. I will not reveal my research on here, as that will dox me completely. So there you go. Hope that's a sufficient answer. Um, Anything else? Okay, I guess I'll just say once again, thank you all for attending. I appreciate you guys attending it. I do apologize for the lackluster work here. It's definitely below par. It's definitely below expectations. Next time, I will do everything to amend it in the next one. So thank you very much. Have a good one. Happy Halloween, and have a good day. Have a good night, day, whatever. Right, see you. Peace.